Alright, so let's talk about Rust, the God's language, according to some. I will say that I like Rust. I don't think that I will say that I love Rust. Here's the thing about Rust. It does really help prevent memory bugs. It prevents data races, but like so many other languages, it doesn't prevent logic bugs magically. Your code can compile, pass all tests, and still be wrong. Let's look at this function, for example. It compiles, Ross is happy, Clippy is happy, and yet it's wrong. What happens if V is empty? You get a panic, a runtime crash. Rust safety guarantees don't help here. What if instead of hoping your tests cover all cases, your code could be mathematically proven correct? Not just tested, proven. That's what Creusot does. Creusot is a formal verification tool. You add contracts to your code, preconditions, postconditions, and empty solvers prove those contracts hold for all possible inputs. Let me show you. So this is a dead simple function, a contrived example, but bear with me. We are adding 1 to a number. What could possibly go wrong? If you are an engineer, I assume you know the answer: overflow. The 64 type has a maximum value, and if we add 1 to the max, we get an undefined behavior. Rust doesn't catch this at compile time. So here's the Creusot version. It adds just 2 lines. That's it. Requires says x must not be max. And by max here, we are referring to the maximum 64 value. And so that's the precondition. Then we have the ensures annotation. It says we need the result to be exactly the input plus 1. That's the precondition. You are probably wondering, what is this at thing? It's the view operator. It converts Rust types to the mathematical model. So I64 at becomes an arbitrary precision integer. Now, the prover can reason about the math without worrying about overflow. When you compile this code with Creusot, you get a green check. This means it doesn't just probably work, it's proven for all inputs that satisfy the precondition. Getting back to our problematic function from earlier, the intent is to access and return the first element from a slice. Again, this compiles just fine. Clippy gives it a thumbs up, and yet it's a landmine waiting to explode. We can sleep better at night by adding a precondition that requires that the slice must have at least 1 element. The v-at symbol converts the slice to a logical sequence. V-at len is the logical length. V-at square bracket 0 is for logical indexing, which is always safe in the logic world. Here's the magic. If this compiles with Creusot, it cannot panic, period. The proof obligation shifts to whoever calls this function. They have to prove the slice is non-empty. So, no more hoping your tests covered the edge cases. No more, what if someone passes an empty slice? Mathematically impossible. Okay, with this example, let's look at loops. Formal verification can be really useful to reason about them. This function computes the sum of 1 to n, where n is any 32-bit unsigned integer. As silly as it sounds for such a simple algorithm, we should ask ourselves, how do we know the implementation of the algorithm is correct. It's a valid question if, hypothetically, this code will be part of some library of primitives that will run on medical devices. With Creusot, besides precondition and postcondition annotations, we can use loop invariant annotations to verify code correctness. In this example, the loop invariant says at every iteration, the sum must equal the closed form formula. You may remember from math class that sum of 1 to n equals n times n plus 1 divided by 2. For this example, the invariant expression uses that same formula with a slight modification. It multiplies both sides by 2 to avoid integer division. You may ask yourself, what is produce that len? It's how many iterations we've completed. Creusot tracks this for you in the for loop. The post condition says when we are done, the result must equal the output of the formula that we just mentioned. Now, because the loop invariant holds at each step and produce that len equals n when the loop ends, right? After the last iteration, produce that len will equal to n. Because of those two things, we've proven that this function will compute the right answer. This function is not just correct for some test inputs. It is proven for all inputs. Let's have a look at a more interesting and hopefully familiar algorithm. Insertion sort, a classic sorting algorithm most engineers have learned. From a correctness perspective, there are two main things that matter. Does it actually sort the array? And does it preserve all elements? By that, we mean to ensure nothing unexpected happens, like duplicated items or some items that inexplicably vanish into a black hole. Typical testing can't prove this for all arrays that are passed as arguments to this current implementation. We can improve our confidence in the code by adding some postconditions. The first postcondition ensures that the output is a rearrangement of the input. No elements lost, no duplicates created. The second postcondition ensures that the result is actually in ascending order. Rust is a good programming language. Some will say it is great. It touts memory safety, data array safety, and a great type system. On its own, however, it's not enough to save you from your skill issues. If you don't believe me, ask the folks at Cloudflare. Rust flavored with some formal verification is your friend, especially if you dream of vibe coding your way to a private jet. Now, should you use a tool like Creusot for everything? No. The learning curve is real, and not everything needs formal verification. You definitely want to use it for critical systems, such as financial systems, medical devices, autonomous drone fleets, and so on. Anything where pretty sure it works isn't good enough. There are other tools like Creusot that give your Rust code superpowers. We will discuss them in future videos. These tools help you put a leash on your AI agents. Even with the vibe coding virus catching on, as an engineer, you are still responsible for delivering code that is correct and works as intended. I decided to make this video because I came across a recent video on Primeagen's YouTube channel where he shows an AI code completion tool he's working on. Based on what he demoed, it amounts to providing enough type definitions so that the agent can handle the implementation details. Generally speaking, what he's building is a program synthesis tool. The evolution of AI is a boon to the field of program synthesis. AlphaCode from Google DeepMind is an example of this. I strongly believe that formal methods will play a significant role on what we can achieve with program synthesis in the future. With that said, you should give Rust and Creusot a try, especially to vibe code your next billion-dollar VC-funded startup. I would like to hear what you think about vibe coding and producing working software. Do you have a proven system that works for you? Is it mostly just a never-ending battle of steering the agents, or have you resigned yourself to embracing the AI slop? Let us know in the comments. So we've reached the end of the video where I do the obligatory please do like and subscribe. So please do like and subscribe. And I will see you in the next one.